So good morning, everybody. My name is Todd Klaus. I'm the lead software engineer for the Kepler Science Operations Center, which is hosted here at Ames. I'll be talking to you a little bit about Kepler, the mission in general, and also how we're doing the processing here, including extending to the supercomputer that you just looked at. This is a time-lapse picture of the actual launch of Kepler. We launched in 2009, so we've been going for almost 3.5 years now. This is our first light image. Is this actual pixel size at this point? Our focal plane is 95 million pixels. Typically, you've got one CCD chip and a digital camera. This is one of our chips, and you've got 42 of these. So we've got 42 CCDs. Each one is split into two halves, two output amplifiers. So we actually get 84 different pictures each time we take a picture of the sky. There's about 6 million stars in that field, of which we are monitoring about 170,000. So let's talk a little bit about what Kepler is and why we're doing this. What we're trying to find is Earth-sized planets in the habitable zone. So the habitable zone is this area around a star where liquid water could exist on the surface. So it's not too hot, too close to the star, it's not too cold where water would turn to ice. It's what they call the Goldilocks zone. And that zone depends on the type of star. So for hot stars, obviously the habitable zone is larger, farther away from the star, whereas sun-like stars, like our sun, is about here in the middle, and cooler stars have a much smaller habitable zone. So we're primarily looking for stars around sun-like stars because we believe that the evolutionary period of one of these stars is most likely to have life. These big hot stars are stars that may be towards the end of their life, and therefore, while their habitable zone is here now, it used to be here, so there hasn't been enough time for planets to evolve around these types of stars. And similarly for these cooler stars, there are also there's a lot more radiation when you're in this close to the star, so that, as far as we know, that's not conducive to life. So we're primarily focused on this, but we're looking for anything we can find in our field of view. The questions we want to ask are these types of terrestrial planets common or rare? And what are their distances from their stars? What are their orbital periods? How many planets are there out there that are in a one-year orbit, like the Earth, for example? And what is their dependence on stellar properties? For example, do these planets exist more often around a certain type of star, like our star, or are they more varied? And the ultimate question is, are we alone? So what we do, what Kepler uses, is called the transit method. So when a planet passes in front of the star, we're not seeing this image and that actual planet. All we're doing is measuring the overall brightness of the star. But you can see that the brightness drops a little bit when that planet passes in front. So we're measuring this brightness, where this is brightness on this axis and time in this axis. And when a planet passes in front, we can see this little tiny dip. And this dip doesn't look like much, but it tells us a whole lot. How often these dips happen tells us how often that planet goes around its star, so we know how long its year is. Using Kepler's laws, we can figure out, how far away it is and whether it's in the habitable zone. The depth of this curve tells you the ratio of the size of the planet to the ratio of the star. So you can figure out, if you know properties about the star itself, you can estimate the size of the star, and knowing that ratio, you can actually estimate the size of the planet. So we get a lot of information out of these light curves. For a planet like Jupiter, crossing the sun, the ratio of that planet to the star is about 1%, so that's like 1 part in 100. You can see planets like this from the ground. In fact, I've actually detected a planet like this from my background observatory in South San Jose. So, but once you start talking about Earth-sized planets, that you're talking about 1 part in 10,000, or about 100 parts per million. This can't be done from the ground. It has to be done from space in order to get it's never been done before. Kepler actually launched. So this is the immense precision that Kepler gives us is what makes it possible for us to detect these little tiny planets. This is where we're looking. Because Kepler is a survey instrument, we're not just trying to find planets, we're trying to characterize for the whole sky, what's the frequency of planets. But because we don't know when these transits are going to happen and how far apart they are, we basically have to stare at the same part of the sky continuously. So that field you saw is the only field we look at. We always look at that same set of stars. And we picked this location we're trying to find a sweet spot between the crowded center. This is the plane of the Milky Way galaxy. There's more stars here, but there's also a lot more dust and contamination. Makes it harder to see the planets. Up here, there's fewer stars, but less contamination, so we kind of picked a spot in the middle there. And then we tweaked this to keep the brightest, closest stars in the edges because they're too bright for our camera to handle. This is the camera itself. So, whereas the image in your digital camera is probably about this big, this one's about this big. It's the largest digital camera to ever fly in space. Like I said, it's 95 megapixels. This is the entire camera itself, the telescope combined. So the mirror is 1.4 meters wide, about this big. Probably bigger than my arm reach can actually reach. There's another lens up here at the front, so all the light comes in, bounces off this mirror, and then hits this focal plane. You can see that it's actually curved to match the curvature of the mirror because it is so big. If you didn't have it curved, things would be in focus in the center and not in focus on the edge. And even as it is, there's a little bit of focus variation as you go towards the edge. It's hard to build optics and a camera this big and keep the image perfect across. But what you saw on that image, we're doing a pretty good job. And this is the entire spacecraft. As you can see, most of it is instrument. The little bottom part here is what handles pointing the spacecraft, the radios, talk to Earth, that kind of thing, keeping it pointing in the right direction. And this is our orbit. Kepler is not in orbit around the Earth. It's actually in orbit around the Sun, trailing behind the Earth. So as the Earth goes around the Sun, Kepler is dropping. It's in a slightly larger orbit, so it's actually getting farther and farther away. It's currently almost 50 million kilometers away, which means that to send a command from Earth to Kepler and to get a response back, even if Kepler responds instantly, it takes a little over 5 minutes to get there and come back. So we don't talk to it in real time. This is some shots of the final assembly of the spacecraft in Florida. They put it in this shroud and lifted it up, popped it on top of the Delta II rocket, and was ready for launch. And this is the actual launch. We did a launch at night, which was really cool. If you never get a chance to see a night launch, I highly recommend it. When the rocket first lit off, this fireball started and everybody started cheering, and then this fireball kind of engulfed the whole thing, and the crowd got a little bit quieter, wondering, is this thing going to pop out? And then it popped out of the top of the fireball, and everybody started cheering again. It's pretty cool. This is a much smaller version of the image you just saw on the board, but this was our first light image we got about a month after launch. Like I said, we have 95 million pixels on our focal array, but we can't afford to either store that on board or download it to the ground because it's just way too much data. There's various methods we use to compress the data, but the number one thing we do is we actually only downlink about 5% of the actual pixels. So before we even take the pictures, we have to decide, number one, which stars do we want to look at? And then for each of those stars, the green marked ones are an example here. These are the pixels we're actually downloading from this particular frame. And you can see for dimmer stars, you may only need like 8 pixels, whereas for brighter stars, you may need a lot more. It's about 32 pixels per target on average for 5.4 million total pixels that we download. The other aspect is time. We're taking a picture every 6 seconds. We're adding those up on board and downloading a co-added image. It's basically every half hour because we need that kind of resolution in time to see those dips in the light curves. The data is downlinked about once a month. It comes through NASA's Deep Space Network, which is used to talk to all space vehicles that are not in Earth orbit. From there, it goes to the Mission Operations Center in Boulder, Colorado, where it then goes to the Space Telescope Science Institute, which is our mission archive. This is where all the Hubble data is kept. And then finally, the raw pixels come here to NASA Ames, where we have the Science Operations Center and the Pleiades cluster to help us with our processing. This is what the pipeline actually looks like. So the first thing we do is we take those individual pixels and we calibrate them to remove things like instrument effects, instrument noise, effects from the optics itself, like vignetting. So we do all that correction. Then we take those corrected pixels for each star and we add them all together. And that's how we get a brightness value for each timestamp for each star. We also do something called pre-search data conditioning, which is correcting, once we have these light curves, correcting a lot of the artifacts that are introduced by the spacecraft and the astrophysics. For example, the spacecraft is getting, the back of the spacecraft is getting hit by the sun and getting warmed, and we found out after launch that that slight thermal change was enough to change the focus of the spacecraft. This is something we didn't think about, didn't realize before launch, but it turns out that Kepler is probably the best thermometer man has ever made. It's measuring very tiny little changes. But that makes our job here harder because we don't want to see those. We're trying to find the planets, not those effects. So we try to filter that stuff out at this step. The back end of the pipeline, so this part of the pipeline we run on each monthly chunk that we get downloaded from the spacecraft, but we're accumulating a big light curves since the beginning of the mission for each star. And it's this part of the algorithm, the transiting planet search, that operates on that aggregate amount of data. So as we're downloading more and more data, this part of the pipeline is getting slower and slower and slower. Right now we're running about 190,000 targets. These are all the targets, all the stars we've observed to date on the mission through the transiting planet search. And the idea is here that this one identifies a subset of these that may be planetary candidates, and that's what we flow into what we call data validation. So of those 190,000, we trim that down to about 15,000. But even of these 15,000, we only think maybe less than half of these are real. The rest are false positives of some kind caused by either astrophysical effects or the spacecraft itself. So what our big challenge now is, how do the humans take these 15,000 and walk through them all and figure out if they're real or not? We're looking at ways like machine learning algorithms, classification algorithms that can be used to simulate what the humans would do if they were going through these manually, just try to speed this process up.
So when you snap a frame, you're imaging all your targets all at once.
That's right. Yeah.
And you're doing that every 6 seconds.
That's right.
But there's no shutter.
Yeah, that's another thing, is because we have a camera that's so big, we don't have a shutter. So, if you know anything about the way CCDs work, they clock the data out. So what you end up getting is smears as those things are read out. And that's part of that pixel level calibration, is to remove that smear effect. We take pictures every 6 seconds, but we can't download each one of those, so we just add every 270 of those images get added up.
So what's the fastest transit you can pick up?
Well, we actually have 2 data collection modes. One is every 30 minutes, and another one for a much smaller subset of targets is every minute, so we can get minute resolution. So if we see something interesting in the 30-minute data, we can put that target on the list for the 1-minute data and see real detail. We're seeing not just finding planets, but seeing really interesting things that stars do. And there's these stars called heartbeat stars, where the light curve actually looks like a heart, which forms the shape of a heart, and this is things that people have never seen before. I wish I had an image to show you of that. But this is why we need Pleiades in the supercomputer here. You can imagine we've got about 8 quarters worth of data now, and it's about 80 billion individual tests that we do on each star. By the time we get to the end of the mission, if we get our extended mission of 32 quarters or 8 years, that's 1.4 trillion individual tests. The good news is that by this time, I think Pleiades will be twice as big as it is now, right?
So you're not able to do it in real time then? You're always backed up? We do it in real time, but we don't do it as often as we'd like to do it. So right now we're collecting data for the 3rd month in quarter 12. We're running pipelines for quarter 1 through quarter 10. But as soon as the data becomes available, we can do that whole processing. But yeah, it's collecting faster than we can actually process it.
So actually, in 4 years at the end of that expected mission, that will be 3 more doublings according to Moore's law. NASA always stayed ahead of Moore's law, so it should be about 10 times.
Yeah. That's what we're counting on. This is a little technical, just to give you an idea of what the algorithm is doing on the supercomputer upstairs. This is the light curve for a single star. This is what we start out with. You notice that these are at different levels. These are from different 30 or 90-day periods. In order to keep the solar panels of the spacecraft facing the sun every 90 days, we rotate 90 degrees, and that moves stars from one sensor to another. And while the sensors are supposed to be identical, obviously there's differences in the response levels. So the first thing we have to do is stitch these pieces together. And we also have to fill in the gaps. Things like not collecting data because the spacecraft is sending information back to Earth. for the algorithms to work correctly, we want to fill that in. That's what these red areas are. So once we've stitched this together and filled in the gaps, we have a light curve that looks like this. Now you may be wondering, there's actually an Earth-size event, Earth-size planet in this data, but looking at it by eye, you wouldn't be able to see it. It's not that clear dip like we saw for that Jupiter-sized planet. So the first thing we do is we take basically a filter, something that looks like a transit, and we slide it across this whole light curve. What we're doing is we're trying to create a metric for each time step. How much does this look like a transit? And that's what this is. So these are marks. The higher the mark you see here, the more transit-like that particular time slice was. But having done that, you still can't see anything in this light curve. It's pretty. The actual signal is smaller than the noise. So the next thing we do is we try to fold these on top of each other. So if we've got two very small transits, but we add them together, the noise tends to cancel out because it's random, but the signal tends to build up. So by folding those things on top of each other, even if you can't see the individual transits, if you fold them all together, then you start to see the actual transit. Because we don't know, ahead of time what the period actually is, we have to try all the periods. So this is a measurement of if you were to stack those what we call single event statistics together, what's the likelihood that there's something every 50 days, every 100 days, every 150 days, for example. And here you can see there's a big spike. This is about a 10-day planet, so this planet goes around its sun every 10 days. So you're saying the most periodic event in this data set is at 10 days. You can then take that 10-day mark back to the original time series and slice it up like a loaf of bread, every 10 days chunks, and then stack those on top of each other. And that's what gets you a light curve that looks like this. So this is all those individual slices stacked together and added up. The noise that's truly random tends to cancel out, it gets smaller, whereas the actual signal tends to augment. You can see this is a really tiny transit, and you wouldn't have been able to know it by eye, but the supercomputer allows us to get to this point.
I have a question. It was
Sure.
about 6 or 8 months ago in a paper they were saying we were getting close to a Goldilocks planet.
Right, and I'll talk a little bit about that,
Yeah.
what we've actually discovered. So this is the number of known transiting planets before Kepler launched. 20 years ago, there were no known exoplanets at all. The only planets we knew of were in our own solar system, and then we kicked Pluto out, so the number was going down. These were discovered mostly ground-based. Observatories found these transiting planets. You notice on this graph, the size is on the y-axis, so you've got Earth-sized planets down here at the bottom all the way up to Jupiter-sized planets. And then along the x-axis, you've got the orbital period in days. So before Kepler, everything we were finding was big and in a very short orbit, what they call the hot Jupiters, really close to their sun, because those are a lot easier to see from the ground. In Kepler's first data set, the first 3 months of data, we had already added all this. So we went from this to this, and these are just the Kepler planets. And you notice that not only are we increasing the number, but we're finding smaller planets, and we're finding planets in larger orbits. The second data release in 2011 made the picture look like this. So now we're actually starting to find planets that are smaller than Earth, and planets in a period, this is a logarithmic scale, so Earth is somewhere around here. So we're starting to push that envelope into this direction. And in December 2011, last year, we added all these extra planets. Now we're up to 2,300 candidates. And you can see, we're encroaching even more into that zone. If we get our extended mission, we hope to extend into this zone, which is where the Earth analogs are. So a planet like Earth, the size of Earth in a one-year orbit would be in this box. And while we haven't found any that are both Earth-size and in the habitable zone, we have found planets that are size of Earth and smaller, and we've found planets that are in the habitable zone. So we feel like we're really close to figuring those two numbers together and actually finding Earth-sized planets in the habitable zone. And I'll leave you, I don't know if any of you are familiar with this iPhone app. It's called, there's one called Exoplanet, which has a catalog of all known exoplanets. Kepler was producing so many candidates that the guy that wrote that app created a special version just for Kepler. And this is a three-dimensional view you can use you can actually scroll around the the view to see from different angles. This is, you can see since Kepler is staring at the same part of the sky all the time, all of the candidates are in this little cone, and they're all fairly farther away. You know, they're probably 3,000 to 10,000 light years away, just because we're trying to, our instrument is so sensitive, we're not looking at the brightest stars, which happen to be the closest stars. Any questions?
I was just at the Cal Academy of Sciences about 3 weeks ago, and this is their latest in their observatory. They showed it, and they showed the.
Oh yeah, yeah.
I don't know if you've had a chance to
I've heard about it. I haven't seen it.
It makes us. I am very not smart when it comes to science, so I was just dumbfounded to see how large the universe really is.
Right. Yeah.
How we're kind of in the Midwest of in terms of all these other planets. Yeah,
Right.
it's really, really eye-opening.
Yeah, and you can get a kind of a feel for that with this app too, because you can zoom all the way out to see the galaxy, and you get to realize how long it takes to zoom all the way in to get to this level. It takes a while.
It's really wild. So
Yeah.
I'm sure. Yeah. Do you feel smaller every single day when you make all these new discoveries?
Oh yeah, it's, you know, there's so much out there, and we're only talking about a little fraction of our own galaxy, right? What's out there in all the other galaxies? What's in the rest of our galaxy? There's the discoveries that are coming out of this data over the next 10, 20, 50 years is going to be amazing.
What's limiting the mission time span?
Two things: propellant on board. We have reaction wheels that are used to point the spacecraft, but there's a constant solar wind against the spacecraft, so those reaction wheels spin faster and faster, and every 3 or 4 days we fire hydrazine thrusters to desaturate those reaction wheels. We've got enough propellant to last maybe 10 more years. The other thing is the spacecraft is getting farther and farther away from Earth, so the bandwidth is dropping. We expect maybe in a couple of years we'll have to drop from 170,000 targets down to 100,000 targets just because of the bandwidth restrictions. But after 10 years or so, the bandwidth drops so low that it's not really feasible anymore.
So what's the reason for not going with the near Earth orbit, the higher Earth orbit, rather than letting it drift off?
There's a lot of because we are so sensitive, things like the day-night cycle of being in an Earth orbit cause a lot of fluctuation. You see how much thermal effect we see just from the constant barrage of the sun, but when you're going in and out of the sunlight, that effect is much bigger. Plus, there's more radiation. You're going in and out of radiation belts, that kind of thing. So this orbit was pioneered by Spitzer, which is an infrared telescope. So we're in the same type of orbit as they are for the same reason, basically. We wouldn't be able to get the sensitivity we're getting here from Earth orbit. Any other questions?
So you didn't really answer it. Have you found one that's like the Goldilocks planet? Because that was the focus.
Right, we haven't found that yet. We've found planets that are in the Goldilocks zone, but they're too big. Like, for example, Kepler 22, which was discovered recently, looks to be about twice as big as Earth. It's in the right place. Surface temperature is probably about 70 degrees. But because it's so big, the gravity would be so high. You could sit on the beach and it would be great, but you wouldn't be able to pick your beer up and actually reach around. So it's not ideal. So we haven't actually converged on that, Earth size and in the habitable zone yet, but we think we're getting close.
So for a planet that big, you can't have it on. It's not just
I have a question for the group, actually. I heard Todd and Chris talk about how Pleiades is crunching all this data, but there's also a way that people can get involved and look at it as well. So I've got a nice Kepler mug. Anybody who knows how you can get involved yourself with searching for planets? SETI.
That's the one.
That's true. SETI is a good answer. There's
Do you also do the folding on PS3?
on what?
The PS3 folding app, I believe it's called.
Oh, I don't know about that one.
That's on the Weve platform, right? That's like the SETI at Home screensaver that you could download. There are other things that will use your computing power, but maybe with that one, you're not necessarily involved yourself. It's just using your kind of background.
Yeah, it
cycle.
uses your background
Yeah.
processing.
So that's, donating your resources, but you can go a step further too.
Yeah.
That's what she's saying.
One step further and actually play with the data yourself and start looking at it. Well, the planethunters.org is a citizen science project that you can go and look at all the data online. And so you use use your computer, you're online, it's a web-based application, and you look for these transits, these dips in the data. And if you find one that's unique, I mean, you get credit for it as well. So planethunters.org is the name of it. So SETI was a pretty good answer, though. So I think it was you who said SETI first. Okay. Well, I have one, but I have 10s and some rogue stickers for everyone. So I can pass those out when you're headed out. But these stickers, you'll notice, these have been around a while actually. And Todd alluded to the history of the mission a little bit, but Bill Barucki, the principal investigator, had this idea that we could witness these transits far, far away using this photometry method. And he started fighting for this back in the mid-'80s, and it took him 5-6 proposals, something like that.
Yeah, and the first paper he wrote was in '84, I think. And
yeah.
at the time, it was, here's an idea that will actually work, but there's no technology that exists that can actually do it. You know, CCDs weren't around back then, so it basically, at that point, he was talking about what could be done, and then CCDs and that kind of stuff came along a few years later, and he actually, put together a proposal for an actual space mission, and it got rejected because people didn't think it was technicit would be too difficult to do, or it'd be too expensive. We actually built a simulator in the basement of one of the buildings over here. They gave us $50,000 of seed money and said, if you can prove that this concept will actually work, then we'll think about your proposal. And that model was an actual, rig model with CCDs and a vacuum chamber. And what we did was we took a little metal plate and drilled little tiny holes, put a light behind it, so the amount of light coming out of that hole was about the same as a star. And then they put a little piece of wire across that hole, and by running a current through that wire, you heat up the wire a tiny bit, makes the wire a little bit thicker, cuts off a little bit of the light, so you can actually simulate an Earth, the volume of an Earth transit. And it was through that mock-up that we were able to actually prove that, yes, this is possible to do. Got the mission approved.
Yeah, so the mission was approved in 2002 or 1.
Something like that.
Yeah. And so it's just a matter of having having it ready, the resources, the money, and so eventually, as you heard, it launched in 2009, but it was expected to launch in 2007. So you'll find on the back of the sticker it says launching in 2007. So it's a little bit of a collector's item too.
Yeah, I started on the project in 2005, and at that point we had no hardware at all. We scrounged 10 surplus PCs from another project. That's how we built the first pipeline. It was just 10 machines that I rigged together and set up. And then we got closer to launch. More people started getting interested, and they actually gave us money and built hardware. Now we're here.
So you're all living in the home of planet hunting. Isn't that cool? It's in your backyard.